We're going to do a quick tutorial on dilution calculations. Well, we probably should start out with some definitions of solution concentration before we do the dilution calculations. By definition, a concentration is an amount per volume. Very often in the laboratory and in chemistry problems, we end up using solution concentrations of moles per liter, and we have converted moles per liter into the term molar, which we abbreviate with a capital M. Other common concentrations derived from that are millimolar, 10 to the minus third molar, or small m, large m, micromolar, 10 to the minus sixth, nanomolar, 10 to the minus ninth. You can also have weight per volume. In some calculations, grams per liter, milligrams per liter, milligrams per milliliter, and so on, depending on the problem you're working with. Sometimes we'll also see units like parts per thousand, parts per million, parts per billion, parts per trillion. And these are very common units used in environmental applications. And if you've ever read the EPA mandated report that comes with your city water bill once a year, you'll see concentrations in these ranges for a variety of differently commonly found components in drinking water. In the laboratory, for convenience, we often make concentrated stock solutions that we can use over many experiments because it's just easier. But when we have these concentrated stock solutions, we'll need to figure out how to dilute these higher concentrations into the lower concentrations that we need for any individual experiment. Well, dilution calculations in reality is just an application of the principle of conservation of matter. What we're doing is we're moving a certain number of moles of material from point A to point B. And the law of conservation of matter simply states that all the moles that we take up from point A must arrive at point B. So typically we can do a concentration in moles per liter, and we move X volume of that concentration in liters. When we do the math, we find out we can solve for the number of moles being moved from point A. Those moles being moved to point B must arrive, and typically we'll have a new lower concentration at a new volume. And of course, liters cancels out, and what we see is, in fact, the moles we started out with at point A have to arrive at point B. Okay, so let's take a look at the basic equation we're going to use for dilution calculations. Dilution formulas will always look like the following. High concentration times small volume equals low concentration times large volume. We usually abbreviate this with C1V1 equals C2V2, where the high concentration is C1, the small volume is V1, the low concentration is C2, and the large volume is V2. When doing these calculations, you will always know 3 out of these 4 variables. Sometimes we'll give you additional information that the small volume is achieved using a piece of glassware called a pipette, or that the large volume is being achieved using a piece of glassware called a volumetric flask. Well, let's take a look at how these dilution calculations play out with word problems. We'll start with a simple one first. We have a stock solution of 6.0 molar HCl and need to make 1 liter of 1 molar HCl for an experiment that we're running. What volume of concentrated acid must we add to the 1 liter flask to achieve the diluted acid concentration that's desired? Well, we're always going to set up an equation that looks like high concentration times small volume equals low concentration times large volume. C1V1 equals C2V2. In this case, when we substitute in the information from the word problem, C1, our high concentration, is 6 moles per liter. V1, the small volume, is what we're being asked to find. C2 is the low concentration, 1 mole per liter. V2 is the large volume, which is the 1 liter flask. If we go ahead and rearrange the algebra to isolate our variable V1, do some units cancellation, and then pick up a calculator, we'll find out that we need 0.17 liters of concentrated 6 molar acid added to a 1 liter flask diluted to 1 liter with DI water to give us the diluted concentration of 1 molar HCl. Let's take a look at a slightly more complex word problem. In an environmental analysis lab, we're testing for trace amounts of a herbicide known as atrazine using an analytical technique called mass spectrometry. To standardize our mass spec, we need a solution with a concentration of 1 micromolar. And the stock solution that we have available has a concentration of 1 millimolar. What volume of stock solution will we pipette into a 10 mil volumetric flask to create the dilute standard to run on our mass spec? Well, the formula always looks the same. C1V1 equals C2V2. 1 millimolar is our high concentration. V1 is the pipette volume that we're being asked to identify. C2 is the diluted concentration, 10 micromolar, and V2 is the flask size, 10 milliliters. Well, if we rearrange for the missing variable, which is V1, we end up with 10 micromolar times 10 mils divided by 1 millimolar. And what you need to identify in this problem is that we have different units of concentration in the numerator and denominator, and those units will not cancel out. So we will need to convert one set of concentration units into another. I've chosen to convert millimolar into micromolar, and a simple Google search will tell you there's 1,000 micromolar in 1 millimolar. Millimolar cancels out. Now I do have the correct identical concentration units in numerator and denominator. Micromolar cancels out. And when I quickly do the math, I find out that I will pipette 1/10 of a milliliter of stock solution into a 10 mil flask, dilute to the mark to get my final desired concentration of 1 micromolar.